to illustrate that, let's take a look at some qualitative examples. Okay. Example number 1. How do you keep your roof from disappearing in a high wind? Suppose there is a roof like this. Okay. This is your house. And here is a high wind, let's say a hurricane, okay, flowing over like this. This can devastate your roof. How does that happen? It's because, look, this is outside, right? The pressure is much lower. Why? Because, there's a high speed, so V is large, therefore, according to Bernoulli's principle, P is small. So you have a small pressure pushing it down, much lower than conventional because of the high wind. But inside, suppose your house is sealed, there is no airflow inside. The pressure is still regular air pressure. And there can be a tremendous difference between the interior pressure and exterior pressure. The net pressure is upward, and if it's strong enough, it can actually lift the entire roof. You see? Okay, so how do you keep this from happening? Well, one of the things you can do is you can open up your doors and windows. You see, if you did that, you allow air movement inside as well, and that reduces the pressure. So the pressure inside is not as great as before. You have lower amount of net pressure pushing up the roof. So hopefully by opening up the doors and windows, you will still have a roof intact when you get home. Alright, now you say, well, I've never been to hurricane country, so I don't have that problem, right? Okay, but have you ever tried to use an umbrella in a high wind? Okay, now an umbrella looks like this, right? Suppose there's a high wind, okay? What happens? Well, chances are that your umbrella might even look like this, right? What is going on here? Well, actually, very simple. The same idea as this. You got a high wind flowing over, so the pressure above is reduced because of the Bernoulli's principle. But inside is a little sanctuary. You see that? There is no air movement because it's trapped. The air is trapped inside. So the air trapped inside has higher pressure because it doesn't move as fast. There is, therefore, an imbalance of pressure that quickly flips it over. And so, this happens to many people. I'm sure you have seen it before. You probably have experienced this before. And that flipping umbrella is also due to Bernoulli's principle. Okay, let's look at yet another example. You know how they throw a curveball in a baseball game? The ball can actually defy gravity. It can momentarily lift itself up as if somebody's pushing it up. How does it do that? Well, in fact, a curveball is thrown in such a way that the ball actually spins, okay, while going forward. For simplicity, let's say we switch to the reference frame of the ball so that the ball is not moving here, the air around it is rushing past it like this, okay? If the ball is spinning, okay, then depending on which direction it spins, you can have an additional air pressure, which can make this a curveball. In particular, if I let the ball spin like this, okay, spin like this, then look at the bottom here. At the bottom, the ball is spinning like this, right? It's spinning backwards, right? That is the same direction as the air movement, right? That encourages the air to flow backwards, so the air pressure, so the air speed would be even higher. What does that tell us? That means the pressure would be lower, okay? Because the higher the pressure, the lower the airflow. The greater the speed, the lower the air pressure. Okay, at the top here, the ball is actually spinning this way, and that is against the direction of the airflow. That decreases the flow speed of the air, and that will increase the pressure. So if you spun the ball like that, you're going to create a net pressure going downwards. Of course, you don't like that. Okay, so how do you throw a curveball upwards? Yeah, all you have to do is reverse the sense of flow. Okay, you let it spin like this, right? Let it spin like this. So at the top, this time at the top, okay, the motion of the ball encourages airflow. The airflow is faster. At the bottom, the ball rotates this way. That discourages airflow. So at the bottom, you have lower airspeed. Therefore, that translates to a greater pressure. At the top, higher airspeed translating to a lower pressure. Therefore, the net pressure is upward, and that's how the ball can defy gravity, at least momentarily, it can go upward. Okay, one last qualitative example is how a perfume bottle works. All right, you've probably seen those perfume bottles, especially in old-fashioned movies. Okay, what you do is this is like a soft pouch. What you do, you can squeeze it. Okay, you can squeeze this part. When you squeeze this part, of course, you allow air to rush out like this, right? And not only is the air rushing out, you also get some fine particles of perfume that you draw out. How does that work? Actually, it's not hard to understand how it works from Bernoulli's principle. The way it is that by moving the air, you have decreased the air pressure at this region. You know, you have decreased the air pressure. Okay, so you have pretty much created a much lower pressure region, and of course, that's going to draw the perfume this way because it's drawn towards lower pressure, right? And so that's how you get a mixture of air and perfume particles. That's how the perfume bottle works. It's very simple. All right, we are now going to look at some actual calculation problems involving Bernoulli's principle. One of the classic examples of the application of Bernoulli's principle is the so-called Torricelli's result. It's named after Italian physicist Torricelli. Consider a large tank of water. The cross-section area is equal to capital A. And let's suppose the depth of the water is h. Now what happens if I open up a small hole at the bottom, and let's say the area of the small hole is small a? You know water is going to rush out, right? Okay, like this. What I want to know is, what is the speed of the water coming out? Okay, what is the speed of the water? How do I solve this problem? You know, when you open up this hole, water is going to leak out, and therefore you have a flow. And therefore we have to use fluid dynamics. The most important principle is, of course, Bernoulli's principle. What does Bernoulli's principle say? It says that if you pick up any 2 points along the same tube of flow, point 1 and 2, then when you add these three terms, P, 1/2 rho v squared, and rho gy, you add these three terms up, you get a constant. Now, let us apply Bernoulli's principle to solve this problem. We're interested at this point, the speed at this point. So that is obviously, this point is obviously one of these 2 points to which apply the Bernoulli's principle. Okay, let's call this point 1. I want to choose another point along the same tube of flow so that I can get this equality of Bernoulli's principle. Where do I choose the other point? Well, you know, water flows like this, right? It flows like this, in fact, like this. I can choose, of course, any point I want along the same tube of flow, but the idea is I want to pick a point wisely, call it point 2, so that I have the most information available about point 2. Do you really want to pick up a point somewhere here or here or here? Well, we don't know exactly the pressure there and so forth, right? Is there a point along the same tube of flow such that I know exactly what the pressure is? Well, yeah, how about the surface? Huh? How about the surface? Let's call this point 2. What is the pressure at the surface? Well, this surface is exposed to the air, therefore the pressure at that point is just the air pressure outside. We call it PA. Okay. Now, let us write down Bernoulli's principle relating point 1 and point 2. For point 1, I have pressure P1, right, plus 1/2 rho V1 squared. V1 is what we're looking for. Plus rho gy. Okay, rho gy y1. Y1 is the height of this point. But of course, I can choose any height I want, any reference frame I want. Let's choose this line to be y equal to 0. So what is y1 equal to? Simply 0, right? Okay, no problem. It equals to P2. P2 is simply equal to PA, right? Plus 1/2 rho V2 squared, and then plus rho g y2. Okay, y2 is the height of that point, and since the 0 level is here, that's just h. Okay, now we're looking for V1. Do we have all the other quantities? Well, we don't know what V2 is, and we don't know what P1 is. Okay, so let's take a look. First of all, what is P1 equal to? What is the pressure at this opening here? Well, you might think, well, this is the depth h below the water level, therefore shouldn't it be equal to P2 plus rho gh? Well, don't forget that formula we got. How did we get that formula? We got that formula assuming that there was no flow, okay? Everything was perfectly in equilibrium and there was no flow. When you have a flow, you cannot do that. You cannot say that P1 equals P2 plus rho gh, because P2 is just PA, right? If P1 equals P2 plus rho gh, okay, you know, you cancel these three terms. One, this term plus this term equals that term. What does that tell you? It tells you V1 equals V2. And that doesn't make any sense, does it? And therefore, we cannot say P equals P initial plus rho gh, because there is actually a flow. As a matter of fact, when you dig a hole here, you have opened up this much water to the air, right? It is no longer sealed off from the air, and therefore, what is the pressure? The pressure should simply be equal to the outside air pressure. Because if the water pressure is higher than the air pressure, then it's going to burst, okay? And if the water pressure is lower than air pressure, air will come in to fill it up. And therefore, PA is equal to P1 as well, not just to P2, because both points 1 and 2 are exposed to the air. So this is PA as well. I can cross that out. Okay, now that leaves me with one more thing here, which is, what is V2? All right, we know V2 is the speed of the water level dropping. V1 is the speed of the water streaming out. Of course, if the area is very large, then V2 is almost equal to 0, right? V2 is almost equal to 0. So as a good approximation, we say V2 is almost equal to 0. Imagine a very large tank with a very small hole. Even if water comes out of the hole, the water level hardly drops at the surface. So this is almost equal to 0, and therefore I have 1/2 rho V1 squared equals rho GH, and that gives me V1 approximately equal to the square root of 2GH. That is known as Torricelli's result. Now, if you take a closer look at Torricelli's result, you'll find something interesting. Basically, if you consider dropping just any object, okay, you drop an object and let it fall freely through a distance h. By the time it reaches the bottom, after covering a distance h vertically, how fast is it moving? Well, isn't that square root of 2gh you learned from Physics 1A, free fall? Okay, so the interesting thing is, if you consider a water particle, okay, you consider a water particle starting from this point, point 2, and moves, following whatever path. By the time it reaches point 1, it has exactly the same speed as if you drop that water particle all the way from here to there directly. Why is that? It turns out this is not quite a coincidence, as a matter of fact. It is actually expected, because after all, what we're using here is Bernoulli's principle, right? The Bernoulli's principle, how do we get Bernoulli's principle? Well, we assumed that there was no viscosity, there was no friction between different layers of the fluid. So it's a non-viscous flow, therefore no mechanical energy is lost. So as this water drop moves from here to there, even though it follows a curved path because it's been pushed around by the surrounding water, the mechanical energy of this drop of water is still conserved. Which means, if you start from 0 speed, nearly 0 speed at the top, after covering a distance h, 1/2 mv squared has to equal to mgh, and therefore you have that final speed. Okay, so you see, the Bernoulli's principle will give you the same result as the conservation of energy because it follows from the conservation of energy. This is the so-called Torricelli's result. Of course, this result is not quite very accurate because we have ignored the fact that V2 is not quite equal to 0 because the water level does drop, even though very slowly. Now, if you want to be more accurate, you don't want to set V2 equal to 0, right? You say V2 is not quite equal to 0, but it's related to V1. Well, in what sense? Remember the continuity equation? You have region 2 with the cross-section area capital A, and region 1 with the cross-section area small a. Isn't it true that V1 times small a should be equal to V2 times big A? Okay, you can actually solve for V2 here. You see, V2 is V1 times small a over big A. You see, it is indeed a lot less than V1 because small a is a lot less than big A, but it's not quite, I'm sorry, this is V2, but it's not quite equal to 0, is it? We plug that back in here, we have a V1 squared here and a V1 squared here. We can actually solve for it. Okay, you get a more accurate result this way, and after you solve for it, this is what you get. You get V1 equal to the square root of 2gh divided by something. 1 minus small a over big A squared. This is the more accurate result. Okay, if you consider the fact that this point 2 actually descends, the water level actually drops. Of course, small a is a lot less than big A, therefore this factor is very close to 0, so 1 minus this is almost equal to 1, therefore this is very close to the square root of 2gh. So this is the Torricelli's result.